Tiffany Bacher, and I'm a junior studying electrical engineering and computer science. I enjoyed the interdisciplinary nature of robotics and took this class because I was interested in learning more about high-level planning and control algorithms. I really enjoyed all of the labs and have learned so much throughout this semester.
Hi, my name is Tim Cardona. I'm a junior studying electrical engineering and physics. I'm interested in a career in data science and signal processing, and the reason why I took this class is to learn more about this in robotic settings.
I'm Jonathan, and I'm a senior in mechanical engineering and controls. I'm taking 6-1-for-1 because I wanted to learn lots of skills that are relevant for my PhD in autonomous vehicle controls at UC Berkeley next year.
I'm Charles Wong, and I'm a sophomore majoring in physics and computer science. I'm interested in machine learning and physics, and I want to learn about control systems. And I'm excited to work with an actual real-world robot.
Hi, I'm Rishi. I'm a junior studying computer science and engineering. I took this class to understand how to integrate low-level and high-level components into a functioning robot. I learned this as well as so much more, and I really enjoyed working with my team.
For our 6-1-for-1 final challenge, our robot had to escape a maze. We implemented two different approaches to this problem, a high-level path planner and a stochastic wall follower. Our first approach started with Google Cartographer, which performs simultaneous localization and mapping, or SLAM, to map the environment using LiDAR data as the robot explores and to localize the pose of the robot. Here, you can see our robot going through a figure 8 track. As our robot receives LiDAR data from its surroundings, Cartographer makes a map of occupied and unoccupied spaces. We then implemented a modified RRT planner to path plan out of the maze. RRT expands a tree graph from a starting point representing viable paths until the graph extends beyond the maze. The RRT tree represented viable turns that the robot can make and avoided obstacles. The planner then finds a path in that tree from the starting location out of the maze. Finally, we use a peer pursuit controller to follow the planned trajectories. In this video, you can see our robot following a trajectory given by a high-level path planner. The blue dot in front of the robot in the simulation video on the left is what we call a goal point. By setting a look-ahead distance, our robot then follows this point, which traverses a trajectory. We used our previous peer pursuit controller to follow trajectories given by our new RRT for this final challenge. The second implementation is a stochastic wall follower that will probabilistically find its way out of the maze. For this algorithm, the robot follows a random wall and switches with some probability after a period of time that was sampled from a normal distribution around a mean of 25 seconds and with a standard deviation of 5 seconds to ensure that our robot will not be fixated on following one wall. Additionally, when the wall follower got too close to the wall, our safety controller would stop it and reverse it out at an angle, which mimics a small 3-point turn as you can see here. On demo day, the first thing we tried out was RRT. Now it is making a 360-degree turn to scope out the maze for Cartographer to make a map. However, this resulted in Cartographer incorrectly marking areas around the robot as occupied. As you can see, our robot went out into the occupied areas and our RRT cannot plan anymore. Fortunately, our wall follower performed superbly, and our car was successfully able to complete the maze in 58 seconds. Due to the random nature of our algorithm, however, our implementation could struggle with dead ends, and there is a high variance to the time it takes to complete the maze. We measured a fastest time of 54 seconds and as long as almost 6 minutes for the same maze setup. In conclusion, our wall follower implementation was simpler but worked well on this maze. With improvements, however, the high-level planner would likely be more robust for larger and more complicated mazes as it can make informed decisions and strategically map to unexplored regions.